Hello, my name is Nicholas Frost. I'll be presenting work by Sarah Sabor, Jeffrey Hinton, and myself. This work was done at Google Brain Toronto. So our paper is about capsules. A capsule network is a new way of doing object recognition that differs from a normal net in a number of ways. Instead of having large hidden layers, we take each hidden layer and we turn it into a number of small capsules. Each capsule has a small activity vector which represents the instantiation parameters of whatever that capsule has learned to detect. Capsules at one layer make predictions via learned transformation matrices for the instantiation parameters at capsules in the layer above. And a capsule gets activated when these predictions agree. So for example, we could have a capsule which has learned to detect a triangle, which could be the nose of a face, and a capsule which has learned to detect an ellipse, which could be the mouth of a face, and these will both make instantiation parameter predictions for a capsule which has learned to detect a face. One big advantage of this, like coincidence filtration as we call it, is that it allows the network to be equivariant. So if we change our viewpoint, then the instantiation parameters for that triangle nose capsule will change, and the instantiation parameters for the ellipse capsule will change, and so will their predictions for the instantiation parameters at the face capsule, but they will still agree, and so the face capsule will still get activated. This differs from a normal neural net because each capsule is comparing incoming activity vectors, whereas in a normal net, each unit is just comparing the activity vector with a learned weight vector. Conversely, if we change the instantiation parameters of the nose capsule but don't change the ellipse capsule, then they will no longer agree, and the face capsule will not get activated. Another advantage of this coincidence filtration is that we can use it, the agreement of these predictions, to route the output of capsules to the appropriate capsule in the level above. So we can do this as an iterative process. On the first iteration, the triangle capsule will weakly send its output to all of the capsules in the level above. And then, if there's agreement in the face capsule, that face capsule will send information back down to the triangle capsule to tell it to send more of its information to the face capsule and less to the other capsules. This iterative process converges after a couple of iterations, and in our example, 3 actually, it converges after 3 iterations, and we're left with a segmentation that groups parts of a whole together. So we created such a capsule network, and we tested it on a variety of data sets, including the MNIST data sets on which we get state-of-the-art performance. We also tested it on a number of other data sets, and we do all right on those ones as well. We also tested it on a data set which we called multi-MNIST, which is just MNIST digits superimposed over each other. So here there's 2 digits, and the object was to detect and identify both digits in the image. We did that because we thought that the coincidence filtration and the segmenting properties of the dynamic routing would make the network very good at this task. And it did. We outperformed CNNs quite drastically on identifying both of the 2 digits in the input. We also added on top of the capsule network a de-rendering or reconstruction network, which we used as both a regularizer and as a way of understanding the instantiation parameters of that top level capsule. So here we have in red and in green the reconstructions of the two digits in the input. So we can see that the capsule network has learned to represent almost everything required to reconstruct those digits just in the instantiation parameters of the top level capsule. And we can also see that it has no problem figuring out which pixels belong to which digit, even when the 2 are highly overlapping. We also tested the network on its ability to be robust to affine transformation. So to do that, we trained on regular MNIST, and then tested on AFNIST, which is MNIST but with skews and rotations and stretches. And we see here that we outperform traditional CNNs drastically on this performance task as well. If you'd like more information about capsules, please come to the Pacific Ballroom number 94. Thank you very much.